So today we're going to be deriving an interesting Taylor series, actually. And actually, usually in these intros, I would talk a lot, but I realized that was more or less kind of the exact same thing. So I'm not gonna waste any time for this video. I'm just gonna go directly in solving this. So before on this channel, if you have actually had the patience to watch, we had these kind of sums before, and it was like a double sum where it was an infinite sum on the outside and then a sum from 0 to n on the inside. And basically what we did was we considered something completely different, and then using summation tricks or summation tactics, we were able to morph that problem into something this form. And more specifically, the sort of problem that we were looking at was the kind of integral, the integral from 0 to x of the product of two functions, f of t and g of t, and then integrated with respect to t. So, if we consider this, now f and g here are already known functions, as in we know their Taylor series representations, and they are the sum n is equal to 0 up to infinity of some sequence an times t to the n, and then g of t is also known. It is, well, it is another Taylor series, and that is n is equal to 0 up to infinity of bn times t to the n. So let's say we know these two functions, right? That they're sort of known, and we know their representations. We know what an and bn are. So what is this integral in terms of an actual sum? So you can imagine, plugging these two definitions in. They're the only sort of thing that we can go off of. So it's a natural step. So we have here the integral from 0 to x, and we get the sum n is equal to 0 up to infinity of an times t to the n, and then this other sum, but we're actually going to combine them into a double sum, basically. But I'm going to write it like this. I want to go n and k go from 0 up to infinity. I think this is pretty standard notation for double sum. And then we have an. So we're going to say that n corresponds to f, and then k is the g index. So an and then bk, and then we have t to the n plus k, and then dt. Alright, so standard thing, we're going to interchange the positions of the integral and the summation. Now here we're assuming that on this integral, on this interval from 0 to x, these two sums converge, meaning that we can actually do this. So we're going to interchange that. The coefficients of our t go out, so we have, this is the double sum. We have n and k going from 0 up to infinity of an times bk, and then we have this integral here from 0 to x of t to the n plus k. The antiderivative of powers are well known, so we do t to the n plus k plus 1 divided by n plus k plus 1, and then we plug in the bounds. So we have here, this is t to the n plus k plus 1 over n plus k plus 1, and then we evaluate that t is equal to 0, t is equal to x, and basically what you do is you plug in the values and then you subtract, right? So if we plug in 0, since n plus k plus 1, since n and k are all bigger than or equal to 0, this thing must be positive, so we wouldn't have to worry about this t equals 0. And in this x case, we just kind of plug that in. So what we actually get is the x as the base, n plus k plus 1, and then divided by n plus k plus 1. Right, so at this point, we're going to rewrite this a little bit. We're going to rewrite this as a sum. N and k go from 0 up to infinity. My handwriting is sort of deteriorating. We have an, we have bk, and then we have this other sequence, c, n plus k. And then the c corresponds to this part. So basically, cn is actually n plus 1 divided by n plus 1. So we have rewritten our sum into this form. Now, that should be familiar because we actually had multiple videos before about this kind of sum. And basically what we did was we took the most complicated argument or the complicated term, and then we index this, or we index this parameter. So basically, I'm gonna write out the sum, right? I'm gonna write out the sum that is equal to a naught, b naught, c naught, plus a1, b naught, c1, plus a2, b naught, c2, and then this goes on. And then this is plus a naught, b1, c1. That's what that sum does, by the way. So it sums over all of n and k being positive, and then plus a1, b1, c2, plus a2, b1, c3, and then plus, and then I'm not gonna write down this third row. I suppose it would make things clearer, but I think it would be mostly just a waste of time. So basically, this goes on and on. So this is an infinite sum. It stretches in this direction as well as in this direction, and its value is this. So basically what we did was we considered a diagonal, and what happens in the diagonal is the c value is preserved. So for example, there's only one diagonal that goes through not, because, well, it's n and k are all bigger than or equal to 0. And then there are two values that go through c1, and it appears on this diagonal. And then there are more terms that go through the c2 term, and that lies on this diagonal. And then we have more diagonals down the line. So we have infinite diagonals. So basically what we do, we sort of diagonalize it, where we consider the c input as the actual index, and we basically factor out these a and b terms. So this is equal to c naught corresponds to only only one combination of a and b, and that's a naught and b naught. And then for c1, there are two options. We have a naught and b1, and a1 and b naught. So a1, b naught plus a naught, b1. And then you then add on c2. We filter out all the c2 terms, and we get a2, b naught plus a1, b1 plus a naught, b2. Basically what it does is it's all of the terms where these indexes sum up to this leading c term. Now this sum, it goes on forever because there are infinitely many diagonals. We can write this in summation notation, and I'm actually going to change something a little bit. So in this representation, for example, the index of a goes 2, 1, 0, and the index of b goes 0, 1, 2. We're actually going to switch that. So basically, we're going to reverse that. So the index of a goes from 1, 0, 1, 2, and the index of b goes 2, 1, 0, because that's going to fit this better. It's going to make it slightly more clear. But it doesn't change because addition, you can swap the places of addition and nothing changes. So basically what this is now we have the sum. We're going to call this c index I. I goes from 0 up to infinity. And then each term has a ci, because that's the index. And then we have this other sum that has I plus 1 elements. And basically, we're going to parameterize it based off of the index of A. So we have j starting from 0 up to n. Because let's take this for example. For C2, the index of it goes 0, 1, and 2. So 0 up to n, we have aj. And then the indexes of a and b must add up to I here. So the index of b must be I minus j. And that's basically what we've done. And now we can sort of bring back the old C definition. We don't need to write things in terms of C anymore. And that will be, this is just the sum actually we're going to write it n in terms of n and k because it matches this thing. So we have the sum n is equal to 0 up to infinity of x to the n plus 1 over n plus 1, right? Very familiar. And then we have this other sum, k is starting from 0 up to n, of these two things, n minus k here. So that's basically what we've done. So basically, this integral of the product of these two Taylor series comes out to a single sum, and actually it's in the form of another Taylor series because it's x to some power and then times some coefficient. So this is what we have so far. Now we're going to plug in this, and what we're actually going to notice is it's in this form. So in terms of this, right, if we call this some other arbitrary function, I've run out of letters or good letters to use. I suppose we're going to do we're not going to do anything. Basically, this function, because this is technically a function in terms of x, we have correspondence for ak. So ak is this thing, this negative 1 to the k over k factorial, because that's the only thing that only has k attached. And then bn minus k matches this n minus k here. That was what I wanted to say. I think I took way too long explaining it. So, what we can do, we can basically reverse this. We can reverse what we've done so far. And I'm actually gonna erase this actually. So we can reverse what we have done so far, and we'd actually get an integral from 0 to x of this first f here, which is an. So a is negative 1 to the k over k factorial. So we get, this is the sum, and then you get a 0 up to infinity of negative 1 to the n x to the, or I mean t to the n over n factorial. We'll deal with the exact form of this in a second. And then we have this other thing, this other sum. Now bk here is just, well, bk is just k, because n minus k, it's the only thing that has n minus k in it, basically. So we have this other sum, k is equal to 0 from up to infinity. This is just k, t to the k, dt. So okay, so we've transformed our infinite sum into an integral. These two sums should be pretty easy to evaluate. So, I mean, this is just an exponential function, basically. So this is e to the negative t. I shouldn't have to explain this. It should be common knowledge at this point. And then we have kt to the k. Now, this is actually something that you could get after you differentiate the geometric series. So I'm actually going to change it a little bit. I'm going to write it as t times the sum, k is equal to 0 up to infinity of k t to the k minus 1. And the reason we're doing that is kt to the k minus 1. This is the derivative of t to the k. And when this sum converges, which I suppose we should put a boundary, actually. We should put a negative 1 smaller than x. Actually, we just put absolute value of x is less than 1. So, in this interval from 0 to x, this sum converges, meaning we can take the derivative of the inside, and that would be the derivative of the sum. So this would be t times the derivative d dt of the geometric series, which is just the sum of t to the k, which is 1 minus t, 1 over 1 minus t. Now this is pretty easy to evaluate. This is equal to t times, this is equal to t times power rule, so 1 minus t squared. We have a minus 1 over here, but because of the chain rule, we get a minus 1 anyway, so we just get 1. So this is t over 1 minus t. So we're kind of cutting corners, especially at this step, but that's basically what it is. So now we can plug this into our integral. We have, this is equal to the integral from 0 to x. T times e to the negative t, we're going to write that in the numerator. And then at the bottom we have 1 minus t squared dt. Now this actually has an elementary antiderivative, and we're actually gonna solve it. It invokes a pretty interesting trick, and that is we're gonna rewrite this fraction, not this exponential, but this fraction. And more specifically, we're gonna write it as the integral from 0 to x, first of all, e to the negative t. We have t over 1 minus t squared, but t is 1 minus t. If we were actually to, I don't know what it's called, but if we bring the minus sign in, the 1 and the 1 cancel, and then we have a plus d over here. So that's a representation for t, I suppose. And then we have a 1 minus t in the denominator, dt. We can split this into two fractions. We get 1 over 1 minus t squared, and then minus 1 minus t over this, but we can cancel the square, so it's just 1 over 1 minus t. So in this case, we'd actually get, I'm not used to writing this down. The integral from 0 to x, first of all, we have an e to the minus t. Yeah, we have an e to the minus t, and then we have this other thing. The first part of this fraction is 1 minus t squared. 1 minus t squared, 1 over that. The second part is minus 1 minus t over this, but like I said, that cancels, so it's just 1 minus t. 1 minus t, 1 over that, dt. Okay, in my handwriting, once again, not that great, especially when I'm writing below here. So I want to make room over here, I suppose, because we don't need this. We've explained everything and we've actually used it, so we don't need this anymore. So now that we have this form, we're actually going to notice that this is the derivative of 1 over 1 minus t, and we've used this before, right? So ddt of 1 over 1 minus t is 1 over 1 minus t squared, so the reverse of that must also be true. So this is actually equal to the integral from 0 to x of e to the minus t times the derivative of 1 minus t, which is 1 over 1 minus t prime. Let me think how I would write that. I think I would do d dt 1 minus t, and then minus 1 minus t, like that. dt. So this integral is now of the form, the integral from 0 to x of e to the minus t times f prime. F is some sort of function of t. F prime minus f dt. And f prime and f are functions, and f prime is the derivative of f. Now, why is this useful? Because, well, now let's consider a special case of the product rule of derivatives. We have d dt. We're using t because it matches that. We have e to the negative t times f, where f is a certain function. By the chain rule, we get e to the negative t times f prime. I'm going to do this first. And then plus the derivative of e to the minus t, but that's minus e to the minus t. So this plus would actually be a minus. Minus e to the negative t f, because we don't have to take the derivative of that anymore. And now we can factor out an e to the minus t, and that would become e to the negative t f prime minus f, which is exactly the form that we have over here. So we can now take the antiderivative of both sides. The ddt would basically cancel, it will go away. We have this antiderivative of e to the negative t f prime minus f is just e to the negative t f with a constant attached to it, but we're actually taking the antiderivative, or no, we're taking the definite integral, so it doesn't really matter. So in this case, what we actually get, the antiderivative of this is actually e to the minus t times this function, and this function we have over here is 1 over 1 minus t. So this is 1 over 1 minus t. And this is this is valued at t equals 0 and t equals x. And this is very easy to calculate, you just plug in the two values. So the antiderivative of this thing is just this. And I suppose you can verify it, but there's not much to verify. It's just the opposite of this step. So now all we have left is just to plug this in. So x, we can do nothing, because, well, x could be anything, so there's nothing much to simplify. We just get e to the negative x over 1 minus x. And then t equals 0. it would just be 1, -1. And that's it. This is a Taylor series representation of e to the minus x divided by 1 minus x and then -1. I suppose you can add this -1 over here, and you will get a constant term, and you will just get this e to the minus. You would just get this e to the minus x over 1 minus x, and that would be a more satisfactory Taylor series. But this is where it comes from, right? So this is basically what it is. And in terms of the actual sum part, I think we've done that before. It's not new. It's old news at this point. What I really like about this is how it involves an interesting insight, I suppose. Because otherwise, maybe you could go about this. You could plug in special functions, but that's not really satisfactory, is it? Alright, I apologize for that. I got interrupted. But I mean, we're basically at the end anyway. I was just gonna say, um, the antiderivative part is, I think, what is most intriguing, because in terms of the series, we've done that before. So that was all I wanted to say. So that basically wraps up this video. The endings of these videos are always super awkward, so I'm just gonna leave it here. I'm gonna say, have a great day, hope you enjoyed, and I have no idea when I'll next upload. So that's it. See ya. Alright, I apologize for that. I got interrupted. But I mean, we're basically at the end anyway. I was just gonna say, the antiderivative part is, I think, what is most intriguing, because in terms of the series, we've done that before. So that was all I wanted to say. So that basically wraps up this video. The endings of these videos are always super awkward, so I'm just gonna leave it here. I'm gonna say, have a great day, hope you enjoyed, and I have no idea when I'll next upload. So that's it. See ya.